Today we're going to talk about exponential decay functions and models. And we touched base on this just a tiny bit the other day, but just remember that an exponential decay function still looks like any other exponential function where we have y equals a times b raised to the x power. A is greater than 0, and our b value is between 0 and 1. That's how we know it is a decay model. So in a function of the form y equals a times b to the x, the base b is the decay factor. Now, graphing exponential decay functions, it's going to be done this exact same way as we graphed exponential growth functions. So all of these exponential functions are graphed exactly the same way. The only difference is that our b value here is going to be a number between 0 and 1. The domain, though, is still -infinity, infinity, and the range is still 0, infinity, and the asymptote is at y equals 0. Now, just like with the other graphs, if we have a shift up or down, that will change the range and the asymptote. If you look at the graph, exponential growth functions, they tend to do this. And you can kind of see that it reflects over the y-axis, but we're not going to call it that or talk about reflecting over the y-axis. We're just going to know the general shape. This green line is an exponential growth function, and the line that is blue here, that is a decay function. So that's how you can tell from a graph if you have exponential growth or decay. So we're going to graph these same way we did the stuff the other day. So our a value is -2. Our b value is 4/5. H, there is no h, and there is no k. So our asymptote is y equals 0. Our domain, -infinity, infinity, and our range, 0, actually wait, no. Because our a value is negative, our range is going to be -infinity, 0. And when we graph this, you'll see that. So we graph x, y, then we have 0, 1, and then 1, our base, which is 4/5. And then we're going to do that second row and multiply everything by -2. So then 1 times -2 is -2. 4/5 times -2 is -8/5, which is going to be close to 2, between 1 and 2. So when we graph that, we're going to estimate that. So 0, -2 is right here. And 1, just a little bit over 1/2 is there. So our graph will look like this. And that would be our exponential function. And again, looking back at the range, when we look back at our y values, they go all the way down to -infinity, and then they get up and approach 0 but never touch 0. And like we had yesterday, our range, asymptote, and k value all match up. All right, now this function over here that we're going to graph, our a value is 3, our b value is 2/3, our h value is -1, because remember, it's the opposite of what you'd see, and our k value is -3. So that means our asymptote is going to be y equals -3. Our domain is -infinity, infinity, and our range is going to be -3, infinity, because our a value is positive. Okay, so we have 0, 1, and 1, 2/3. And then we're going to multiply everything by 3. So 1 times 3 is 3. 2/3 times 3 is going to be 2. So when we graph that, and yes, this graph is going to go off the page a little bit. So let's just plot 0, 3, and 2, 1. But remember, we have to now move each point left 1 and down 3 based on our h and k values. So left 1 and down 3. 1, 2, 3. Let me use a different color. Let's put 1, 2, 3. Remember, our asymptote is at y equals -3. So 1, 2, 3. Here's our asymptote. So then I'm going to use the light blue ones for our graph. And there is what the graph of this would look like. Now let's look at the next page here. And just like what we did yesterday, we have an exponential decay model, and you'll notice that it looks exactly like the growth one, except that this symbol is now a minus sign. And what you'll need to be able to determine is which formula do we use based off of the problem or the situation. So one of the words you want to look for is like decrease or decay or goes down by. That would tell you that you would use the subtraction one as opposed to the addition model. And A and R and T are all the same thing. A is that initial amount, R is a percent increase or percent decrease as a decimal, and then that B value would be 1 minus R. But I just like to tape it all into the calculator at once, but you don't have to do it that way. So letter A says, write an exponential decay model giving the television's value, y, in dollars after t years. So y equals, we started out with 1,200 times 1. And since it says decreased by 21%, it's going to be minus 0.21 raised to the t power. We can simplify this right here and then write it as y equals 1,200 times 0.79 to the t power. And then we can just plug in t to get our answer. Identify the initial amount, the decay factor, and the percent decrease. Well, we already did that. The initial amount was $1,200. The decay factor, it went down by 0.79. That was right here. And the percent decrease, that came from the problem itself. Estimate the value after 2 years. So we're going to plug in 2 for t. So 0.79 raised to the second power. So in the calculator, we're just going to type in 1,000 times 0.79 raised to the second power, and we get 748.92. Now when we're asked to graph the model, we have 2 points. We have 0, 1,200. And then we have right here from letter C, 2, 748.92, which we can just say is really close to 750. So 750 would be about there. So the graph would look like this. Use the graph to estimate the value, or when the value of the television will be $300. So we'll go to $300. That looks like between 5 and 6 years. So that's what we write, between 5 and 6 years. So that is it for the exponential decay lesson. So thank you for watching. Make sure to like this video and subscribe.